been my pleasure working with this team this semester. And I do want to say that it's rare that we can boast. I boast all the time, but it's rare that we can really honestly boast that engineering is the most holistic discipline, because they have been perfecting the racing thing on the college athletics, and now their senior project has been about racing, boat racing, solar powered electric boats. So I'm gonna hand it over to Josh Guy and Johnny Guy and their Solar Splash powertrain design. Thank you.
Hello everyone, thanks for coming. Like Dr. Field said, I'm Josh Guy, and this is my partner, Johnny Guy. And our presentation today is over the Solar Splash powertrain design. Our advisors for this semester were Dr. Field and Dr. Cuban. So the objective of our project was to design and operate a lightweight, efficient, and powerful drive system that will increase the speed of USI's 2016 Solar Splash boat. So to begin with, a background of the Solar Splash competition. It began in 1994, and it's considered the World Championship of Intercollegiate Solar Electric Boating. Now each team at the competition presents and operates a solar-powered boat. The size of this boat is limited to 6 meters long by 2.4 meters wide. It can only be powered by solar energy. However, storage of this solar energy in the form of 3 12-volt DC batteries is allowed. You must have a minimum of 100 watts of solar energy that's supplied by solar panels attached to the hull of the boat. And there's no restriction on the drive system so long as that no human power or wind power is used to propel the boat. Finally, all fasteners on mechanical systems must have lock washers or Loctite on them. So each design is based on workmanship, visual appeal, and performance. It's a 5-day event held in Dayton, Ohio, and it consists of 3 different races shown on the bottom side. They are the solar slalom, the endurance, and the sprint race. Now, solar harvesting is allowed at the beginning of each day from the opening competition until the last event has finished. So on the left here you see the solar slalom. It's worth 100 points possible. It's a timed event, meaning that one boat competes at a time. And the course is designed so that each boat has to weave in and out of buoys placed in the lake. The middle event you see is the endurance. It's weighed the most. It's 400 points possible. It's a 2-hour event in which the officials measure the amount of laps that each team completes, and the team that completes the most amount of laps is awarded the most amount of points. In this far right picture is the sprint competition. It's a head-to-head drag race. So you are racing another boat right next to you, and it's worth 250 points possible. It's just a straight shot from the dock to the finish line. Here's a subsystem breakdown of our 2016 Solar Splash boat. Now, last year was the first year of USI competing in the Solar Splash competition, so they had to focus on all of these subsystems you see up here. Last semester's senior project focused on the gauges under operator controls, and this semester's project is focusing on the power source and the drive system shown in this red box to the right. So here's a picture of the existing design shown right here. You can see the solar panels are mounted above the driver on a PVC canopy. This was done to minimize the shadow cast by the driver onto the panels. And in this bottom picture is the layout of all the components of the boat, including the steering system, the throttle, the solar charging controller, the 3 DC batteries, the motor controller, and the motor and outdrive mounted on the rear of the boat. And these red rectangles are one of 4 solar panels mounted on the canopy. So the existing outdrive is based on an outboard motor design shown in this right-hand picture. The electric motor is shown in this gray cylinder right here with the output shaft going downwards, and it's coupled to the drive shaft, which travels through this orange picture here. And then the drive shaft goes into the lower unit of the outboard shown in this left-hand side picture. And the the lower unit of the outboard was taken off a 9.9 horsepower Mercury. And inside of this is a ring and pinion system, which transmits the power from the drive shaft to the propeller shaft here. So there's various issues with the existing design, the main one being that the top speed of last year's boat was roughly 7 miles per hour. The motor chosen for last year's competition was rated for 5,000 RPM. However, this was at 96 volts, and we are limited to 36 volts, so it's severely underpowered. Because of this, the motor is only producing a little over 2,000 RPM, and at the propeller, this equated to about 1,075 RPM. The motor was only drawing 24 amps of current, and after multiplied by the torque constant, this equated to 3.6 newton meters of torque. So all these factors contributed to the low speed of 7 miles per hour. There's also no ability to trim the outdrive up or down, and by trimming, I mean tilting the outdrive up or down to adjust the angle of the force vector produced by the propeller. Some requirements of the new motoring controller that we selected were that it had to be more applicable to our 36 volt restriction for our competition, and we were looking for a more programmable controller for testing purposes. This year we chose an ME0909 DC brushed motor shown in this picture here. This decision was based on cost, torque, RPM, and weight. So when looking at different motors, we were looking for one that had the least amount of cost, produced the most amount of torque, RPM, and weighed the least amount. We coupled this motor with an All-Trax SPM 48300 controller, and an important aspect of this is that it is easily programmable with free software available for download on Alltrax's website. So when choosing a motor, we analyzed different torque curves for all of our different options in order to determine which one was the best suit for our application. So here it is the torque curve for our choice, the ME0909, and some important data that can be taken from this curve so that the efficiency is right at 90%. The RPM varies from 2,800 to 3,400, and the max power is just under 5,000 watts. So in designing an outdrive, we considered 3 different choices. They were the inboard, shown on the left, the outboard, pictured in the middle, and a surface drive unit, shown on the right. Now, in order to decide what type of design we were going to go with, an in-depth decision matrix was constructed and placed in our technical report, but for visualization purposes, a simplified version is shown here. In the blue, these are our criteria for our design. They were efficiency, drag, estimated cost, steering modification, hull cutting, and trim. So we wanted an outdrive with the highest amount of efficiency, produced the least amount of drag, cost the least, had the least amount of steering modification, the least amount of hull cutting, and had the ability to trim. So we chose a surface drive, which is shown in the bottom here. As you can see, it excels in the efficiency, drag, and the ability to trim due to the fact that it operates half in and half out of the water, so that there's not as many mechanical components dragging in the water. This results in a higher efficiency and lower amount of drag. So when talking about surface drives, there's 3 different types. You have your outboard style of surface drive shown on the left, the articulated shaft design shown in the middle, and the fixed shaft shown on the right. We chose an articulated shaft design due to the fact that we wanted it to trim up and down and steer left and right without the addition of a rudder. So after choosing a motoring controller, we had to design some sort of way in order to distribute this power to our drive shaft. There were 2 different ways that we considered doing this. First was the direct drive, and the advantages of a direct drive would be that it's very simple. You just couple the output shaft of your motor directly to the drive shaft. The disadvantages of this was that there's no manipulation of the RPM. So your output RPM of your motor is precisely what you get at the propeller. Since we wanted to increase our propeller RPM from our motor RPM, we decided to design some form of gearing. We chose a pulley and belt system over a gearbox design or a chain sprocket due to the lightweight, low cost, and ease of installation. We can change the diameters of our pulleys to achieve different gear ratios. And after we did our calculations, we calculated 8.4 horsepower per belt. And since our motor is capable of up to 12 horsepower peak, just to be on the safe side, we designed a 2-belt system. So that's why it's 2 grooves in this pulley seen here. And we wanted a gear ratio of 1.3 to achieve an RPM of 4,300 at our propeller. So the driving pulley is slightly smaller than the driven pulley. The tensioner was also incorporated to ensure that proper tension was had at all times in each of the belts. Since we went with an articulated shaft design, we needed some sort of CV joint to allow the drive shaft to pivot to side and up and down for steering and trim. So we needed a CV joint or constant velocity joint, and we chose one off of a 2004 Honda TRX 450 ATV. It's off the front axle. An important component of this was that the CV joint is not rated for axial loads. This will come into play later on in the design. The rest of our drive shaft was a 3/4 inch stainless steel drive shaft, and this resulted in a factor of safety of 19, so it's well over-designed for our application. However, we chose 3/4 inch due to the fact that it's a common propeller shaft size, so it's very easy to put a spline on the shaft and install our propeller on the end. 2 roller bearings were selected for this shaft. Each had a max RPM of 7,800 and a max dynamic load of over 6,500 pounds of force. Also, we chose these due to the dimensions of the shaft, and the outside diameter of the bearing would fit in our drive shaft housing. Now, like Josh said, our CV joint that we selected was not rated for axial loads. So we needed to design a way to distribute this force away from the CV joint. Normally, as the propeller spins, it exerts thrust on the drive shaft, and our CV joint is connected to the drive shaft. So we distributed this force by designing several components, the first of which was a stepped drive shaft, shown in the picture. And then we also designed a drive shaft housing, also shown. And inside this housing, there is a collar in which the stepped drive shaft rides on. In between the step on the drive shaft and the collar in the drive shaft housing is a thrust roller bearing, also seen in the picture. Both of these are being fabricated in the AEC. Now from there, the thrust is distributed to a ball and socket joint that we also designed. This is shown in the lower picture. We designed this type of joint in order to accommodate for the trimming of the motor as well as the steering. Now the thrust bearing that we selected was a TC1220 thrust roller needle bearing, and we selected this due to its high dynamic load rating of 2,900 pounds force, so well above our needs. It was the correct size for our 3/4 inch drive shaft, and it was at low cost and high availability. Another objective of our design was to enable the current cutter to plane, and by planing I mean that the hydrodynamic forces of lift outweigh the buoyant forces of lift, and correct trimming facilitates this. For the most efficient operation, the thrust should be directly in line with the center of gravity. So we measured our center of gravity of the current cutter to be 163 inches behind the bow, 0.15 inches starboard of the center line, and 20 inches above the boat floor. Now trimming down facilitates planing, as shown in the bottom picture, because as you trim the motor down, the thrust is angled above the center of gravity, which depresses the bow. So in order to trim our outdrive, we selected a linear actuator with a 12-inch stroke. It was 12 volts DC, and we added a tab to our drive shaft housing in order to connect this linear actuator to. It was selected due to its high capacity of lift of 175 pounds, well over what we're expecting. Had a 16¼ inch retracted length and 28¼ inch extended length, so plenty of room to allow our outdrive to trim. And the user controls this with a switch mounted next to the steering wheel. It was desired to use as much of the existing steering system as possible in order to drive down cost. The existing system is shown on the left. This is a rack and pinion system. As the user turns the steering wheel, the cable extends or retracts. So in order to use this existing system, we designed a rope and pulley system, shown on the right. The pulleys are mounted at each corner of the rear of the boat, as shown. And as the steering cable extends or retracts, it pulls the outdrive right or left. Now, an extension spring was added to this design in order to maintain correct tension with various trim. Propeller selection was also a very important part of our design. We knew we needed a surface piercing propeller due to we were designing a surface drive, and this is the reason for the increased efficiency of a surface drive. Now, a normal submerged propeller operates by creating an area of low pressure behind the propeller, which creates a thrust in the forward direction. Now, surface piercing propeller operates half in and half out of the water. Problems arise whenever the low pressure area behind the propeller reaches the vapor pressure of the water. So the water forms water vapor. Now these water vapor bubbles collide with the propeller, and this results in a loss of efficiency, power, and can cause significant propeller damage. The surface piercing propeller eliminates this by operating half in, half out of the water. So with each stroke of the propeller, it brings in a pocket of air next to the propeller. These air pockets are compressible and eliminates the act of cavitation. So we selected a signature performance cleaver propeller. In order to do this for us, we selected this due to the fact that it was designed for a 9.9 horsepower Mercury, so right within our horsepower range. These propellers are characterized by sharp leading edges and thin trailing edges, as you see. This is a picture of the complete outdrive assembled. Not shown here is our steering system, which would extend in and out of the page right at the tab on the drive shaft housing in order to turn the outdrive right and left. Up top we have our linear actuator, which would allow for us to trim the boat up and down. On the back is the ball and socket joint. Inside this joint is where the CV joint is located, and this is mounted to the stern. This is our drive shaft housing, which houses the drive shaft, and on the end is our surface piercing propeller. Now we also conducted a drag test in order to quantify the amount of forces that our design would be susceptible to. We did this by towing the current cutter behind another vessel at constant speeds and measuring the tension force in the rope. Now this tension force is representative of both frictional and wave-making drag. The frictional drag is corresponding to the friction between the boat and the hull, and the wave-making drag is due to the amount of energy required to create the wake behind the boat. So our drag data is linear up to 20 miles an hour, and at a speed of 20 miles an hour, we experienced a 110-pound force tension. Now we use this data to construct several different strategies. The first was for our endurance race. Now we knew the amount of power required to propel the current cutter at various speeds, so we factored in the charging of the batteries due to the solar panels, a 75% propeller efficiency and 90% motor efficiency, and it was determined that the optimum velocity to travel in order to get the furthest distance was 8 miles an hour. Now we also plotted battery depletion versus velocity for our sprint race due to the fact that the solar panels would not be connected to the hull. So at a speed of 20 miles an hour, we experienced a little under 3.5% battery depletion. We were awarded an Endeavor grant of $2,500 this semester, and at the bottom you see the budget for our project. It's a little over $2,000, so the remaining of this grant is being used for materials related to the competition, but not specifically to our project. And also our labor is listed to the right. So the remaining schedule of our project is we plan to test our boat on May 14th, and the Solar Splash competition is June 15th in Dayton, Ohio. We would like to acknowledge Donna Moore, Justin Amos, Dr. Field, Dr. Cuban, Endeavor, and the entire Solar Splash team for all of their help this semester. So in conclusion, a lightweight, powerful, and efficient powertrain system has been designed and is being fabricated in preparation for the 2016 Solar Splash competition. At this point, we'd like to open it up to any questions.
All right, questions?
I might have missed this, but what's the status of your fabrication of that thing?
Well, these pictures show what we have done currently. We have the ball and socket joint completed, and we're just starting on the drive shaft housing.
Thanks, Josh and Johnny. Have you been able to test your pulley system? Your belt system, excuse me?
No, not currently. We do have all the pulleys and the belts, and we do have the motor spinning, but we haven't installed the motor into the boat at this time.
All right. Any other questions?
I really like the graph about how fast you go and how that affects your total distance. What is that, what was it based on? Is that a calculation?
Yeah, it was a calculation based off the amount of force that we experience due to drag, and so it's based off of when the batteries would be depleted. So that's why we can't travel at 20 miles an hour and last the entire 2 hours. So at a speed of 8 miles an hour, the batteries would be depleted just at the end of the 2-hour endurance race.
Thank you, that's really good. Thank you.
On your battery depletion chart there, are you taking into account any concurrent charging that you might experience while the boat's out on the water, or can you even do that?
Well, we plan to disconnect the solar canopy from the hull during the sprint race due to the fact that it's not really needed for that short of a race, and it would cut down on weight.
But I mean the endurance race.
Oh, the endurance race, yes. During the endurance race, this is including the solar panel charging.
Okay, so our max speed last time was 7 miles an hour, but around 8 is about optimum, you're thinking?
Yeah, so last year, their max speed was 7 miles an hour, even for the sprint race. So what that graph shows is that to travel the furthest distance, we want to travel 8 miles an hour in the endurance race. However, hopefully, we will be able to travel a lot faster than that in the sprint and the slalom races.
Okay.
I'm curious about your trimming function. What is do you have an approximate angle of up or down movement? And is there a maximum amount of color that can actually go into the water before you have a negative effect, whether it be in the surface mount or the surface drag?
So the trim will have to be adjusted in operation. So as the boat enters plane, the hull will rise out of the water. So that's part of the reason why we want to be able to adjust the trim in operation. So that will be sort of a testing advantage where you will have it trimmed down to start off, and then you can trim it up as the boat enters onto the plane. And to add to that, with our linear actuator, we have a 30-degree angle of trim in both directions, and the propeller that we selected, it can operate fully submerged, but it just most efficiently operates at half in and half out of the water.
All right. Any more questions? Let's give them a hand.